Hello and welcome, everyone. My name is Dane Menke. I am the Digital Marketing Manager here at Regenesis and Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please try refreshing your browser. If that does not fix the issue, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we do not address your question, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we'll be sending out a brief survey following the webinar to get your feedback. Today's webinar will discuss a site in which a combined in-situ biogeochemical reduction solution rapidly mitigated a threat to a nearby river and saved the client $380,000. With that, I'd like to introduce our presenters for today. We're pleased to have with us Scott Connors, Senior Geologist at Wilcox Environmental Engineering. Scott Connors has over 20 years of experience in the environmental consulting industry as a geologist. At Wilcox Environmental Engineering, he's involved in all phases of site investigation and remediation, including proposal, bid acquisition, permitting, monitoring, installation, analysis, and reporting. He is responsible for managing large and complex projects from the point of initial consultation and preparing client proposals to the oversight of fieldwork, ranging for permits, monitoring progress, and providing analysis and reporting upon completion to clients, attorneys, insurers, regulatory officials, and other various stakeholders. We're also pleased to have with us today Brett Hicks, Central Region Manager at Regenesis. Brett Hicks has 15 years of experience in the environmental industry. In his current role at Regenesis, he leads a team of technical remediation experts across the Great Lakes, Ohio Valley, and southeastern regions of the United States, delivering solutions for sites contaminated with PFAS, chlorinated solvents, and petroleum hydrocarbons. Brett's team assists environmental engineering and consulting firms, as well as responsible parties, in achieving their site goals using cutting-edge colloidal technologies. He has extensive experience in-situ chemical oxidation, bioremediation, chemical reduction, and carbon sorption. We're also pleased to have with us today Todd Harrington, Director of Product Management at Regenesis. Todd Harrington is dedicated to driving product innovation that is beneficial to remediation practitioners and the environment, and providing industry-leading support to Regenesis clients. He has over 25 years of environmental remediation experience, primarily focused on in-situ remediation. He has been involved with thousands of contaminated site remediation projects during his tenure at Regenesis, and has expertise with enhanced bioremediation, chemical oxidation, chemical reduction, and carbon sorption. All right, that concludes our introduction. So now I will hand things over to Scott Connors to get us started.
Well, hello. Thanks, Dan. I appreciate that. Hi, everyone. Like you said, my name is Scott Connors. I work at Wilcox Environmental Engineering here in Indiana, and got a pretty cool little project to discuss with everyone today. It was brought to us about 4 years or so ago. It's in downtown Indianapolis, in what is commonly referred to as the 0153 groundwater contaminant plume. It's a large number of commingled chlorinated solvent sites, dry cleaners, machine shops, you name it, there's a lot of it. So downtown Indianapolis is it's kind of riddled with a lot of stuff, and this was one of the ones that the stakeholders brought to us to get fresh perspective on. The previous consultant just wasn't moving along as quickly as they wanted to, and they wanted to get some fresh eyes on it. So they brought it to us and asked us to take a look and see what we would do to fix the problem. So we took a look at the site, all the data that existed, and it was a challenge from the very get-go, just because of the depth and the length of the dissolved plume. It was primarily TCE and its breakdown or daughter products in the groundwater, and it was flowing generally south towards the White River. So we have a lot of potential receptors on this one. The chance for vapor intrusion along a good number of businesses that the groundwater is flowing beneath, and also the ecological portion where it was heading towards the river. So again, when we first got the project, we kind of stepped back and looked at everything and tried to figure out what our data gaps were. The first portion was the regulatory authority had concerns about the basal portion of the groundwater area, the stratigraphy of the site, and the glacial outwash that we're in. They weren't convinced that we had an impermeable aquitard at the base. So our first portion, we went out there and did some additional investigation with a geoprobe from the area near the river and then all the way up the transect or the spine of the groundwater plume to verify the depth of the aquitard. And we encountered it generally between 30 and 38 feet below grade. And we found out that it was ubiquitous across the project area. So we knew that the chlorinated solvents, again, primarily TCE, even if there was any residual free product, that it wasn't going any deeper than that, 35, 38 foot zone. So that was our first gap that we had to fill, was knowing the vertical extent of the problem. The existing monitoring well network was fairly well established. We put in a couple of additional wells so we could have longer screens, just so we could sample at multiple depths and determine the exact thickness of the dissolved plume. So we went out there, continued groundwater monitoring the site. We switched over to using passive diffusion bags, or PDBs, to collect our samples. Seemed to be a little bit better, and we could, again, sample at multiple depths. And for a fairly inexpensive groundwater sampling, low flow tends to generate a lot of purge water, so we were trying to minimize costs for our client by switching the sampling technique. The regulatory authority was all on board and fully in favor. And to verify that we had good correlation from one sampling technique to the next, we did split sampling. We put the PDBs in the well, retrieved them about 2 weeks later, and then sampled those, and then also did low flow sampling so we could verify we were on the same order of magnitude. So we were very comfortable with the data that we were getting. So we kind of had an idea of the extent of the problem at this point. And then when we spoke with the stakeholders about their goals for the site, they said, we want this project done. We want to get closure. It's been going on for far too long. We want to see an end to the site to get the no further action from the regulators. So that's what we set out to do. We started looking at the problem. Again, groundwater plume in sand and gravel aquifer, in river outwash, glacial outwash above a nice till plain. While a lot of different remedies would work, they were cost prohibitive. For instance, typical old multiphase extraction, is it possible? Yeah, but you'd be pumping millions upon millions of gallons of water and probably not get a very good capture zone. So we were able to rule out a good number of technologies from the jump. The other issue was the source area. While the business was no longer in operation, so we didn't have any additional releases, we did still have a continuing source feeding the groundwater. That was in the upper area just beneath the former operations at the factory. So we had absorbed chlorinated solvents still stuck to the silty clay soil that was a continual source to the groundwater. So we had basically two issues to treat. The first one, the source area, you cut the head off the snake and eventually the body's going to die. So we had to, also kind of bisect the body with another technology. So we looked at its site, kind of, what will work, and then we looked at the cost after the fact, because the marching orders were solve the problem. So we teamed up with Regenesis to look at the long cigar-shaped groundwater plume that was, had already left the property. And we had another teaming partner, TRS, to help us design a thermal remedy for the source. Based on the silty clay stratigraphy beneath the site, we knew injections wouldn't work. It was too tight. We wouldn't get the, lateral dispersion and the contact that we wanted, so we could take care of the source. So it was a nice opportunity to kind of showcase our ability to do a combined remedy. So we did thermal at the source, and we decided upon injections down gradient along towards the river. So after looking at it and what would work, got a hold of my good friend Brett at Regenesis and said, all right, buddy, let's have a talk, because we got a project to work on together again, which actually kind of made him kind of happy. So we sat down one afternoon over tacos, looked at the site and said, okay, this is what I need from Regenesis. What do you need from me to help you? So there was a couple of different things that we started to do because we didn't know the full thickness of the dissolved plume. So Brett mentioned to me these cool things he had, or that Regenesis had, called flux tracers. So we deployed those in some of our newly installed monitoring wells. I'll let Brett talk about that in a little bit. He's a lot more knowledgeable on their inner workings than I am. But we did use the flux tracers so we could really get a good handle on the thickness of the groundwater plume, not just by using PDBs at a couple different depths. We wanted to know exactly where the contaminants were traveling, and we also needed to determine the groundwater velocity or the flow velocity through the site area, because it would have potentially had an effect on our ability to thermally treat the source. If the water's moving too fast, you're not going to get the heat that you need to treat the source, and it would essentially either fail, or we'd have to engineer an extremely expensive system on the upgradient side of the thermal area so we could slow the groundwater flow. Turns out that with flux tracer data, we didn't need to do any additional work in the source for the groundwater because the flow velocity was much slower than we had originally estimated. So that was good news. So the flux tracer data was wonderful. We convinced the stakeholders that even though it's spending a little bit more money, it's going to get us some good quality data. And on the grand scheme of this project, what we had an idea the price was going to be, this was a drop in the bucket. So it was either going to be, a little bit of money wasted, which we didn't want to do, or it could be a little bit of money that ends up saving thousands, which it turns out it did. The data we got from the flux tracers and the additional groundwater data that we had allowed us to reduce the amount of injectables that we needed to purchase from Regenesis and subsequently put in the ground. So less material and less time on site, ended up saving about $380,000 off the price of the remediation for the site from what we initially estimated. So we spent about 35 or 40 grand for the new well install and all the flux tracer data, and we saved 380 and made our stakeholders extremely happy. So we came up with this plan with, again, the thermal and then the injectables with Genesis, had a nice long meeting with the state regulators, said, this is our plan. We don't see anything else that's going to work, and get rid of this problem quickly. They loved the idea. We went down and toured the site, and everything went well. They brought out their risk assessors, their chemists, their geologists, the project manager himself, and just had a great plan. So we had stakeholder buy-in from our client, the client's council, the state regulators. There were no objections to the plan. Then we presented the price to the client, and they said, that's a lot, but you know what? If that's all it's going to do, that's all it's going to work, go do it. So we quickly got the stakeholders to commit to the price tag and authorized our proposal. So we sat down, put pencil to paper, come up with the plan, and next thing you know, we're out there with Regenesis and we're injecting. We started, I want to say it was end of October a couple years back, and we ended up middle of January. And got to give a shout out to the guys at Regenesis and their contractors. Our last day was our worst weather day in Indiana. We had about 8 inches of snow, and the guys said, nope, we're going to finish this job today. Which was wonderful. I like seeing that kind of attitude from our field crew. So again, hats off to those guys. They did a real great job and finished the job incident free. I think we ended up putting in around maybe 450 injectant locations. So it was a lot of work and all done safely by a fantastic crew. The other thing that we needed to make sure was that we were going to get the contact that we wanted to get with the injectables that we put in there. So, and that's another thing that I think Brett will talk about in a little bit is some of the design verification sampling that we do. If you're putting in the injectables, is it going where you want it to go? Are you getting the lateral dispersion that you want? Brett will talk about that, but we were able to prove, we got a shadow of a doubt that we were hitting our target zone perfectly across the board. And then after the injectables were completed, about a week later was when we turned the thermal system on. So we went right from one remediation technology into the next, which was, again, perfect. Was a very well thought out, well planned project. And we went out, I think it was about 30 days post injection, which kind of matched up perfectly with the first quarter sampling event. So while we were still treating the source, we were able to do our typical sampling. We were hoping to get a 30-day sample so we could check to see how quickly the injectants were working, and it was like night and day. Some of the graphics you'll be seeing here shows the plume at the beginning of the project prior to injectant, and then the first quarter post. It's incredible results. We ended up putting 1, 2, 3, 4, 5, I think it was 6 injectant lines perpendicular to the groundwater flow, and the samples that came back for the first quarter, some of them we went from very high concentrations in the low hundreds parts per billion of TCE to non-detect within 1 quarter. It was absolutely just incredible. So we continue to monitor the site. Another one of these maps you'll be seeing here shows the comparison of the first quarter prior to injection, and then the most recent 3 quarters of sampling. And the saying, a picture's worth 1,000 words. You take a look at this and you look at how bad the problem was, and now you can see how little residual TCE we have. Now it's still out there, it's not all gone yet, but as the groundwater flows through the barriers that we installed, it's treating it. So while we still have a little bit near the source, which one would expect, it's cleaning up exactly how we wanted it to. So the work we come to expect from Regenesis, we continue to get, and they continue to deliver. I think that's a good little summary of the site. I think Brett's going to expand a little more specifically on like I said, the technologies that we use, the flux tracers, how they worked, and the suite of different injectants that we use at the site, because it varied across the site based on the geochemistry and what our goals were. So I'll turn the webinar over to Brett now so he can expand a little bit on Regenesis and their work. Thank you.
Thank you very much, Scott. I appreciate it. So with that, I'm going to get into a little more detail of the site specifics and some of the technologies utilized here. So thanks, Scott, for giving a good introduction here. So just getting into a little bit more background about the site itself, it was a former chemical manufacturing facility that conducted photo engraving processes from the 1950s all the way up through 2004. So a long tenure there on the site. But unfortunately, with a lot of the site practices, as we know, can generate some pretty long plumes. And in this case, we generated about a 1,500-foot-long chlorinated solvent plume headed towards a large surface water body that was flowing through multiple shallow and deep zones within this aquifer. So there were a lot of challenges presented on the project. And so circling back to Scott's comment when, him and I first sat down to discuss this site over tacos, there was a lot of things that jumped out as we went through this project, but I wanted to highlight a few of the concepts that Scott highlighted as key components of a remedial solution that he was looking for. We needed a flexible approach from a logistics standpoint. It was a very challenging site in an urban setting, as you saw from the figure earlier. We had a lot of offsite properties, a lot of municipal roadways that we had to work with. We needed to immediately halt the migration of this plume as it was migrating towards the surface water body. So that was a key component there. We wanted to minimize daughter product formation. We were primarily dealing with TCE, so we wanted to mitigate that in the best way, most efficient way possible without generating daughters, at least the least amount possible. Then ultimately, it needs to be cost effective. We hear that a lot, and in this case, it was a very large plume, so nobody expected this thing to be a bargain price, but we still needed to be as cost effective as possible with ultimately achieving our goals. And the last one was kind of the most important, as Scott highlighted, was rapid treatment. Both the end users and the site property owner was ready for this to be done. This had been going on for quite some time. They were ready to wrap this up. So those are the key ideals solutions that we're trying to work this proposal. And so I'll get into a little bit of how we got it done. So the challenge kind of talked about that a little bit. We had a good understanding of kind of how big this thing was, some of the plume features, but we really didn't have a good understanding of the granularity of it and the inner workings of this plume. So we wanted to really focus in on those migration pathways where this plume is being distributed throughout that zone. And as I mentioned earlier, we also were challenged with the multiple roadways, buildings, and where we were actually able to even access to install our permeable reactive barriers to cut off this plume. So those are the primary challenges we were facing. It all starts kind of with the in-situ process here. I want to stepwise through this, but it starts with the design verification testing. So the remedial planning started when Scott and I were discussing it at the very beginning, and that's just kind of very conceptual. Then when we get into the design verification, we have to verify actually, what are the assumptions that we made, are they accurate in the field itself? And all this work is done working very closely with the consultant and Scott in this case, because nobody knows the site as well as they do. So all of this process that you're seeing here is something that we do working very closely in conjunction with the consultant. So what is DVT? I want to highlight kind of what that is and what that process looks like for us. So DVT is a process of data collection and analysis, verifying our assumptions in the field. Localized high density sample collection, in this case, primarily trying to identify the contaminant transport zones, the flux zones. Where's that mass moving? And it's primarily necessary because if we think about site investigation data, which is really what the site has conducted so far, a lot of that data, it has different goals than what we're looking for from a remediation design perspective. Site investigation, we're typically looking for nature and extent. How bad is it and where's it going? Who's it affecting? Which is all very important for us as well. But we also want to know what's going on in the interior workings of this thing. And that's what we really focus on with our design verification. And that's really just trying to ensure the most accurate and efficient placement of our reagents and making sure they get to where they need to go, and ultimately trying to have the most successful project that we can. For this particular talk, I'm going to focus mainly on the flux tracer and the mass flux vertical profiling tool that we utilize, because it was a big player of this remedial program. But first, let's take a look at, what is mass flux, right? So flux is proportional to flow, and it really doesn't matter what it is that we're looking at, right? It could be the amount of light passing through a given area, through a window, right? So traffic moving through an intersection, that's all flux, right? But from our perspective, we're concerned with the amount of groundwater and contaminants moving through a given area. That's what we're primarily focused on when we're looking at flux, and in this case, mass flux. So as mass flux, as we're looking at it from a remedial scale, we'll take a look at this particular site here. We can see the groundwater here is our groundwater plume is moving through our source zone. We have contamination. What we see here is varying amounts of contaminants are being picked up as that groundwater is moving through there and flowing along with groundwater. So that heterogeneity in the subsurface and the aquifer is actually allowing for a heterogeneous flow of groundwater. So we have less contaminants moving through some areas and more contaminants moving through others. And what we get here, we have a picture showing those varying contaminant concentrations layered on top of each other. So if we look at just individual well samples, we're not getting a clear picture of what that actually is going to be across our site. We're just getting a general average, right? So it's kind of giving us an incomplete picture of our conceptual site model of the area that we're trying to remediate. So why is that important? So why is measuring mass flux important? It's extremely important because, as a lot of folks will realize, is 80% of our mass is flowing through only 20% of our aquifer. So, identifying the mass that moves is really crucial to fully understanding and being able to remediate our mass and delineating those vertical zones that are ultimately controlling the size and shape of our plume. Permeable reactive barriers, which is the tool we utilize in this particular instance, are extremely sensitive to contaminant mass flux in relation to both short and long-term performance. Without fully understanding the mass flux and where it's moving, we run the risk of underdosing or not dosing our PRBs accordingly and jeopardizing the performance of our PRBs over time. So Getting into the design verification program that we implemented specifically for this particular project, as I mentioned, our primary objective is we were trying to identify those flow channels throughout our treatment zone. And we did this in a few different ways. So first off, we went out, as Scott mentioned earlier, we collected a baseline groundwater geochemistry round, and utilizing some installation of some temporary piezometers and some new monitoring wells, collected a baseline to see where our starting point is. We also collected some soil cores to confirm our lithology, and as it changed from the source site as it moved towards the river, there was some ondulation of that aquitard that Scott mentioned from the site all the way down to the river. So we need to be able to identify where that is and what those fluctuations were to be able to target the interval that we intended to target. And then lastly, we utilized the flux tracer devices, which you can see. I have a snip of the cartoon here on the right. Flux tracer devices are stainless steel canisters that are pre-assembled by our laboratory services that are filled with a granular activated carbon that are deployed into your existing monitoring wells that help us get a good understanding of the Darcy velocity and the mass flux flowing through our treatment zone. We installed 5 of these, 5 15-foot devices throughout the center of this plume, one in each barrier location. From that figure that we showed earlier, we had one passive flux meter in each barrier. So what are those results? What do they show for our particular instance here? So of the 5 15-foot devices, it really allowed us to identify those mass flux zones. Straddling that 15-foot treatment interval, we can really see where that mass is moving through. One of the key takeaways we had here, and Scott touched on it briefly, is we were able to firm up the groundwater velocity assumptions that were made. So when we very first started this, there was a lot of data dating way back from when this site was first brought to the regulatory community of an estimate of 1,200 feet per year, which is really fast. So there's a big difference between that and what our actual calculated velocity was, being 300 feet per year utilizing the flux tracer devices. So that allows us to dose those PRBs accordingly, and there's a big difference between 1,200 and 300 on dose and how much we would actually be required to arrest this plume. But it also allowed us to optimize our vertical dosing. So we were able to hone in of the areas within that vertical treatment interval where that mass was actually moving and dose that a little bit higher in some instances than some of the zones that may not be moving much contamination at all. So we were able to get the reagents where they needed to be to achieve our ultimate remedial goals. Then the last bullet, horizontal plume. So we conducted some additional delineation on the horizontal side and honing in on where the main bulk of this contamination was moving from a horizontal standpoint. And that resulted in a decreased overall barrier length of about 44%. So when you combine all that together, there was a great reduction from our initial assumptions based on some design verification field activities that resulted in about $380,000 of saved money for the client in the overall remedial plan. So clients really like saving money. So if we can convince them to spend a little on the front end to save a good deal on the back end, it's a win-win for everybody. So getting into the actual full-scale approach following our design verification, we were able to revise our design, go into the field. We did do a kind of a 2-tiered approach, combined remedy with the on-site component up near the source, utilizing a slow release electron donor and a soluble ferrous iron to mitigate anything bleeding off from that source material prior to hitting the first PRB, consisting of a colloidal activated carbon or plume stop technology and our sulfidated S-micro ZVI for the remainder of the 4 barriers for the off-site application. So as we move to the field, that conceptual site model continues to evolve. So once we're in the field, we're always confirming and adjusting, right? So on the plume this size particularly, there's a lot of changes that need to be made in variations along that plume. So see, these are some of the tools that we utilize in the field, conducting pre-injection soil cores and temporary piezometer placement for each injection zone, so we can verify that we are seeing the distribution that we expect to see during our actual injection application. This allows us to collect real-time groundwater samples from those temporary piezometers in proximity to an injection point and actively monitor those geochemical response within those piezometers. Following the injection confirmation there, we'll collect a confirmation core on the back end, and you can see here, in this particular case, we were targeting that 15 to 26 foot interval And you can see the visible black staining throughout our targeted treatment interval. So we know we were seeing the horizontal distribution via the temporary piezometers, and then with collecting the soil core confirmation core here, we can see we also had the vertical saturation throughout our target treatment interval, which is exactly what we want to see. This is just a little closer shot of that same soil core. You can really see that black staining in our target treatment interval, and that's exactly what we're trying to look for. And if we don't see that, I'd like to say they all come out looking like that, but that's not always the case. But these confirmation cores really allow us to adjust our volumes, our injection concentration as necessary to make sure that we are achieving the overall distribution and throughout our target treatment interval. So just to kind of wrap up the full-scale PRB approach and kind of some of the numbers that are associated with that, as I mentioned, it was a two-tiered approach with the on-site ERD and the off-site colloidal activated carbon plume stop. We did all this work in the latter part of 2022, wrapping up in the first part of 2023. As you can see, conducted 56 days through the winter of Indianapolis. As Scott mentioned earlier, we were pretty fortunate with the weather in this particular application, outside of a couple snowstorms. But overall, we were pretty fortunate with some pretty decent weather in the winter. But we applied about 110,000 gallons across the site in those 56 days. And a highlight here on this table here below is just to show the annulation and the difference of our treatment intervals through the 4 PRBs as we moved from the site down to the river. So there was a lot of changes throughout that zone that was very important for us to be able to confirm throughout the program of each PRB location to make sure that we were hitting our target interval and placing that remedial fluid where it needed to go. So getting into the results, Scott briefly touched on some of these. I mean, they're really looking really good and pretty impressive overall. And 3 months post-application, we went out and collected our first round. We saw an immediate dose response, 80 to 100% reduction in total VOCs throughout our target interval along that plume. Then as we start to work through, this has been sustained for 3 quarters and counting at this point. So we're continuing to see the degradation occur, and this plume is really shrinking up, and the overall threat to the White River has been mitigated overall. So this is a combination slide of all 4 before and after photos, so I think they kind of speak for themselves. The results are really impressive. The client's happy, regulatory body's happy, all good things there. So in summary, I want to go back and take a look at the original goals that Scott and I outlined at the very beginning, and how we can check the boxes for all of these, and developing a flexible approach, utilizing our PRBs that allowed us the flexibility to minimize our disruption to a very busy area of Indianapolis. The results show, we've been able to halt that plume migration to the river. It's no longer a threat to that river. We minimized the outer product formation. We not only eliminated that TC, but we did not see any daughter product creep. All good things. Cost effective. We ultimately saved the client $380,000 in the long run. So yeah, everything's looking really good with the rapid seizure of that plume. Regulatory body's happy, and we're headed towards the monitoring phase of this program. So hopefully we'll be updating everybody soon with a closed site and on to the next one. And with that, I will turn this over to Mr. Harrington to wrap us up and get into the colloidal technologies a bit. Thank you.
All right, thank you, Brett, for that great information and case study. I'm going to give a very abbreviated overview at this part of the presentation of the technologies used, some of the highlights before we get into the Q&A. And what I want to talk about first is plume stop, which is kind of the workhorse for the barriers that we talked about. It's a colloidal activated carbon. It's very small, 1 to 2 microns in diameter. It does give a view of something like an ink, as shown in the drawing on the right. But what's unique and what was used very effectively on the sites that we talked about is that it's small enough to move through the pore space of an aquifer and evenly coat that aquifer. So it gives a nice even coating. The comparison shown in this, we've used this before, but this set of images is the plume stop moving through under gravity flow, under low pressure in a sand column compared to powdered activated carbon on the right. So this is excellent for creating a barrier system. Now, once in place in the subsurface, it does absorb out contaminants. That reduces the contaminant concentrations very quickly. It minimizes down gradient flux, and in of itself can have a multi-year lifespan. But over time, what you really want to do is you do want to destroy the contaminants that are adsorbed to it to extend the lifespan even farther and prevent breakthrough. And the first way that we've done that in the past, it wasn't the primary method we used on this case study, but we do use enhanced reductive dechlorination with electron donors. Now, I'll talk about an electron donor we did use in the source area in a bit called 3DME, but in the barriers themselves, we can regenerate. First, we've done it through biodegradation. And when that happens, the destruction of, say, PC or TCE frees up absorption sites where those new incoming contaminants can absorb over time. Now, the same thing can be done using a non-biological approach, say using the iron product that we talked about, the S-microZVI, through chemical reduction via beta elimination. So this is a commonly used graphic, and I'm going to put it up here just for the benefit of our viewers who may not be as familiar with either biologic dechlorination or abiotic dechlorination. On the top row, that is the classic sequence of the reductive dechlorination process as PCE moves all the way to, say, innocuous ethene. And this is typically done by adding an electron donor and or adding also for stimulation a microbial consortium. We have one called BDI that I'll highlight in a minute. So that is the biodegradation pathway. We can also go through beta elimination, which is the use of our iron product. Now, what that did in the barriers is it sidestepped daughter product formation. The top row, dechlorination through biodegradation, can be prone to the buildup of daughter products, which could break through a barrier, whereas an S-microZVI is extremely fast at degrading PC and TCE and sidestepping that daughter product formation. So the product that was used more in the source area, it wasn't the main highlight of our talk today, but I just wanted to mention that it's an excellent product that's been out for a number of years. It can be used with the plume stop or the ZVI. It's a 3 to 4 year lifespan, 3-stage electron donor comprised of lactate, polylactate esters, and free fatty acids. There's excellent distribution, and we've used it very successfully. We often pair this with a bacterial culture called Biodechloroinoculum Plus. Again, this has been out for a while. The use of such a culture has been ongoing for a couple decades. We find it very effective as well to go ahead and add this anytime we add electron donors. And that's what was done on the upper source area and some of the initial parts of the barriers that we had in this case study. But it's relatively inexpensive. We don't put a lot in, and it's a really good safety factor. But the heavy lifting for destruction of what we talked about today was S-microZVI. The challenge with the ZVI is that when you just add iron, it rusts. And when it rusts, it passivates. And you have a decreased persistence and less treatment of the contaminants. Our answer has been to sulfidate the surface. And what does that mean? That means to add an iron sulfide outer layer. I'm not going to get into the specifics of how it's done, but suffice it to say that once you add a layer, it's a protective layer that prevents the iron from rusting. It minimizes the reaction rate with water and maximizes the amount of electron transfer rates that can be used for dechlorination of the contaminants. So it has much greater longevity and reactivity. In fact, in a lab study that we did, we can see that 150 micromoles of TCE on the vertical axis is completely destroyed in about 15 days, whereas the same type of iron in the same situation barely destroyed the TC at all. And so what we're finding is that S-microZVI is about 30 to 50 times more reactive than bare iron and still has a 4+ year longevity. All right, I'm going to just show a couple slides here that show the synergy of these products, that show how important it is to put them together. So, just making the case, as I've done with the previous slides, that with sorption only, what we're looking at is actually the model output of plume force, which is a model that we have internally that we use to model dose rates and performance, et cetera, and we can explore synergies of our products. This is a centerline output for this model that shows concentrations on the vertical axis in micrograms per liter, and horizontally its distance in feet, and the gray bar is a barrier. This could be like the barriers that we talked about in the case study today. And as you can see, let's say we run this for 7 years at 200 feet a year. We have a solvent plume going from left to right through that barrier and out of it, that it's insufficient in of itself through sorption only to stop contaminants from making it through over the long run. So that's why, because it doesn't effectively sorb everything over time, we added the S micro-ZVI to our barriers, or to the case study that we did. And what you can see right here is that because the S micro-ZVI, has 30 times the reaction weight of normal iron, you can see the PCE in blue and the TCE in orange drop quickly in concentration. In fact, no breakthrough whatsoever. And really, because it's sidestepping the generation of vinyl chloride and DCE, you're also not seeing any of those products appear in that barrier, and it's completely effective on its own there. Now, one thing we have the option to do with, say, 3DME is there could be situations where we have a lot of vinyl chloride coming in, we have a lot of DCE already coming in, and that would be a situation where we would add an electron donor and even the biodechloroinoculum to really give sort of the state-of-the-art, most highest performance that we can get. And you can see in this barrier here, there's absolutely no concern of breakthrough by any of the parent or daughter products, superior performance of the vinyl chloride. So just a snapshot of what we can do, putting things together. And with that, I'd like to turn it back over to Dane, and I appreciate your time.
All right, thank you very much, Todd. So that concludes the formal section of our presentation. At this point, we'd like to shift into the question and answer portion of the webcast, as Todd mentioned. Before we do this, just a couple quick reminders. First, we will be sending out a brief survey after the webinar. We really appreciate your feedback, so please take a minute to let us know how we did. Also, you will receive an email with the recording as soon as it is available. All right, so let's circle back to the questions here. Here is a question for Scott. Scott, the question is, what other technologies did you consider and why did you choose the Regenesis technologies?
When we're going through our remedial design, we kind of go through, all the typical ones. Can you dig it up? Yeah, you could. Is it cost effective? No. Could you use mechanical means, with an older style multiphase extraction? We don't do that so much anymore because we found better ways to treat the plumes, so ruled that one out. Soil vapor extraction, not really. We had too many properties to deal with, and also we wouldn't get the stripping of the TCE just because of how widespread it was. So we just kind of go through the exercise of saying what will work, what won't work, but is it cost effective? And when it came down to it, it was the source treatment, like I mentioned earlier, and then the products that Regenesis uses. It wasn't a hard sell for me. I've used Regenesis, I can't count the number of times over the past, 10, 15 years or something like that. And I've never had a failure. So, while you guys have competitors who make similar products, they're not as good. I've found, a company I like working with, a team I trust to help, make my clients happy. So it was just pretty much that simple. I guess experience with you and your crew, and knowing how all your products work, and just letting the client know that this is the way to make this happen. You want closure, this is what we're going with. So it was, again, a very easy sell.
All right, so here is another question here. It is, can these products be used in fractured bedrock?
I can take that one. Yeah, so absolutely you can use these in fractured bedrock. The idea is that it also depends. I mean, we've seen a number of such. We actually have a number of case studies on our website where we've done successful applications in fractured bedrock. The key to success really lies in a good geophysical survey. What we need to find out is, are, say, bedrock fractures interconnected? What are the size of the fractures? Things of that nature. And if it's determined at that point that there is interconnectivity, that, by putting a series of, say, open boreholes with packers or monitoring wells, colloidal technologies transmit quite well within these environments. So the answer is yes. And in fact, we've seen some pretty large radius of influences within bedrock where we have good interconnectivity. But I want to say that really the key is that initial investigation, it's hard for us to say that we could do a site, and often they require some sort of initial injection testing just to verify everything.
All right, thanks, Todd. So here's another question for Scott. Scott, the question is, how did the regulators view the remediation plan? Were there any hurdles that you needed to overcome for that?
No real hurdles to speak of. Like Brett mentioned, we had a couple of logistical things in the field we had to deal with, weather, stuff like that. But as far as the plan, no, they were pretty much sold after our first meeting. They looked at it, and again, the two technologies, the thermal for the source, Regenesis's injectables for the down gradient. That was the plan that made the most sense, and they bought off on it pretty quickly.
All right, thanks, Scott. So here's another question here. It is, let's see, what concentrations can you handle with your products? And are you able to remediate DNAP?
Yeah, I'll take that one, Todd. I know we hear this quite often, but it's very site specific, right? And that gets back to utilizing the flux tracers for contaminant concentrations. We really need to understand how much is there, how high are those concentrations, and more importantly is how fast are they coming to our treatment zone. We can treat some pretty high contaminant concentrations if we have the residence time to keep those contaminants in our treatment zone long enough to be able to treat them. And then with regards to DNAPL, and that's one that it's really a site-specific standard on its own. In most cases, we're not trying to degrade DNAPL. That's where we're looking to physically remove it in some fashion, as in this case where we teamed up with TRS and the thermal component to go in there and remediate the DNAPL via some sort of physical removal or heavy hammer.
Okay, thanks, Brett. So here's another question for Scott. Scott, the question is, what additional characterization was necessary to make sure the injections would take care of the dissolved plume?
Okay. Well, actually, that was kind of something that Brett kind of touched on with using the flux tracers. Again, we went out there with the geoprobe, took some additional soil cores. Being a geologist, I can't treat something I can't see, so I wanted to put my eyes on the soil type we were dealing with. So just again, additional visual characterization for me, and then using the flux tracers to get our flow velocity and the contaminant thickness distribution. So I guess that was long and short is, geoprobe, soil cores, additional groundwater samples from the monitoring well network, and then the flux tracers.
Okay, thanks, Scott. Here's another question. It is, what would you suggest for a site where the groundwater plume also contains PFAS? How would the approach described on this site handle that, if at all?
Yeah, absolutely. I'll take that one as well. So really, the applicability of the technologies utilized here would transition very well to a PFAS program. Plume stop has been demonstrated on many sites to be effective at mitigating PFAS. Now, the degradation mechanisms are not there, so the zero valent iron and the ERD side of things would not be at play from a PFAS standpoint. But the use of our plume stop technologies and other colloidal carbon technologies are certainly applicable in a PFAS mitigation strategy.
All right, so here is another question for Scott. Scott, the question is, how did you convince your client to move forward using the flux tracers to help characterize the site?
It was again a fairly simple approach. We kind of laid out the cost benefit. I want to spend some of your money, but I think I can save you a lot of money. We had came with a plan after talking with Brett, knew what the installation and analysis costs would be, and in the grand scheme of, again, what this project cost, the amount we wanted to spend was a very, very small percentage of, initial out costs, with the benefit being potentially saving hundreds of thousands of dollars. So again, with the amount of injectant that we didn't need to put in the ground, saved them $380, and we spent about $35. So to me, that was not good at math, but that's a pretty good percentage. So it was, they were very happy with that. And again, you spend a little, get good data so you can make good decisions.
All right, so here's a question regarding the Regenesis colloidal products. Can you explain more on your design process and the type of sites where you would use the various combinations of colloidal products?
Brett, that might be a little back and forth on that, and it's a good question because there's a lot of flexibility on what we can do. But the first thing that we look for is what is the flux of contamination coming through? What's the mix of that contamination? What's the concentration ranges, which is built in the flux? And then we make an assessment on what do we need to do. But what we always do here at Regenesis is we try to run these through our simulations so that we can predict what's coming through, and then we can change the proximity, the locations. There's a lot of flexibility to really tune it, just more that we could get into today. But Brett, I don't know if you wanted to add anything to that or not.
Yeah, I'll build on that a little bit as it relates to Scott and I's relationship. Regenesis has a very wide and great toolbox, if you will, and Scott and I has developed a pretty good use of that. And we have a nice series of projects that Scott and I have worked on together over the last several years, utilizing a combined remedy approach, very similar to what we've done here today. That's proven successful across the state of Indiana on many sites. So to what you said, Todd, and that's looking at each site differently and finding the best tools for that particular scenario has proven very successful for Scott and I on several different sites.
Okay, thanks guys. So here's another question for Scott. And Scott, the question is, what was the main objective of the project stakeholders?
So here we go. Yeah, the answer to that question is very quick and simple. It's closure. They wanted no further action on this project. It had been going on a little longer than they had wanted it to, and they wanted to see the end to it. So again, in a word, closure.
All right, so thanks very much. That is going to be the end of our chat questions. If we did not get your question, someone will make an effort to follow up with you. If you would like to learn more about services from Wilcox, please visit wilcoxenv.com. If you'd like to learn more about remediation technologies from Regenesis, please visit regenesis.com. Thanks again very much to our presenters, Scott Connors, Brett Hicks, and Todd Harrington. And thanks to everyone who could join us. Have a great day.